Static routing. Static routes with next hop addresses. As we have discussed previously, a router can learn about remote networks in one of two ways. Manually, from configured static routes. Automatically, from a dynamic routing protocol. Static routes. Static routes are commonly used when routing from a network to a subnetwork. A subnetwork is a network accessed by a single route. For an example, see the figure. Here we see that any network attached to R1 would only have one way to reach other destinations, whether to networks attached to R2 or to destinations beyond R2. Therefore, Network 172.16.3.0 is a subnetwork and R1 is a stub router. Running a routing protocol between R1 and R2 is a waste of resources because R1 has only one way out for sending non-local traffic. Therefore, static routes are configured for connectivity to remote networks that are not directly connected to a router. Again, referring to the figure, we would configure a static route on R2 to the LAN attached to R1. We will also see how to configure a default static route from R1 to R2 later in the chapter so that R1 can send traffic to any destination beyond R2. The IP route command. The command for configuring a static route is IP route. As shown in the figure, we will use a simpler version of the syntax. The following parameters are used. Network address, destination network address of the remote network to be added to the routing table. Subnet mask of the remote network to be added to the routing table. The subnet mask can be modified to summarize a group of networks. One or both of the following parameters must also be used. IP address, commonly referred to as the next hop router's IP address. Exit interface, outgoing interface that would be used in forwarding packets to the destination network. Note, the IP address parameter is commonly referred to as the next hop router's IP address. The actual next hop router's IP address is commonly used for this parameter. However, the IP address parameter could be any IP address, as long as it is resolvable in the routing table. Installing a static route on the routing table. Remember, R1 knows about its directly connected networks. These are the routes currently in its routing table. The remote networks that R1 does not know about are 172.16.1.0/124, the LAN on R2. 192.168.1.0/24, the serial network between R2 and R3. 192.168.2.0/24, the LAN on R3. First, enable debug IP routing to have the iOS display a message when the new route is added to the routing table. Then, use the IP route command to configure static routes on R1 for each of these networks. The figure shows the first route configured. Let's examine each element in this output. IP route, static route command. 172.16.1.0. Network address of remote network. 255.255.255.0, subnet mask of remote network. 172.16.2.2, serial 0/0/0 interface IP address on R2, which is the next hop to this network. When the IP address is the actual next hop router's IP address, this IP address is reachable from one of this router's directly connected networks. In other words, the next hop IP address 172.16.2.2 is on router R1's directly connected serial 0/0/0 network 172.16.2.0/24. Verifying the static route. The output from debug IP routing shows that this route has been added to the routing table. Notice in the figure that entering show IP route on R1 shows the new routing table. The static route entry is highlighted. Let's examine this output. Routing table code for static route. 172.16.1.0 network address for the route. /24 subnet mask for this route. This is displayed in the line above, known as the parent route, and discussed in Chapter 8. 1/0 administrative distance and metric for the static route explained in a later chapter. Via 172.16.2.2, IP address of the next hop router, the IP address of R2's serial 0/0/0 interface. Any packets with a destination IP address that have the 24 leftmost bits matching 172.16.1.0 will use this route. Configuring routes to two more remote networks. The commands to configure the routes for the other two remote networks are shown in the figure. Notice that all three static routes configured on R1 have the same next hop IP address, 172.16.2.2. Using the topology diagram as a reference, we can see that this is true because packets for all of the remote networks must be forwarded to router R2, the next hop router. Use the show IP route command again to examine the new static routes in the routing table, as shown. The /24 subnet masks are located on the same line as the network address. The static routes that have been configured can also be verified by examining the running configuration with the show running config command. Now is a good time to save the configuration to NVRAM. Routing table principles. Now that three static routes are configured, can you predict whether packets destined for these networks will reach their destination? Will packets from all these networks destined for network 172.16.3.0/24 reach their destination? Let's introduce three routing table principles, as described by Alex Zenon in his book, Cisco IP Routing. Principle 1. Every router makes its decision alone, based on the information it has in its own routing table. R1 has three static routes in its routing table and makes forwarding decisions based solely upon the information in the routing table. R1 does not consult the routing tables in any other routers. Nor does it know whether or not those routers have routes to other networks. Making each router aware of remote networks is the responsibility of the network administrator. Principle 2. The fact that one router has certain information in its routing table does not mean that other routers have the same information. R1 does not know what information other routers have in their routing table. For example, R1 has a route to the 192.168.2.0/24 network through router R2. Any packets that match this route belong to the 192.168.2.0/24 network and will be forwarded to router R2. R1 does not know whether or not R2 has a route to the 192.168.2.0/24 network. Again, the network administrator would be responsible for ensuring that the next hop router also has a route to this network. Using Principle 2, we still need to configure the proper routing on the other routers R2 and R3, to make sure that they have routes to these three networks. Principle 3, routing information about a path from one network to another does not provide routing information about the reverse, or return path. Most of the communication over networks is bidirectional. This means that packets must travel in both directions between the end devices involved. A packet from PC1 may reach PC3 because all the routers involved have routes to the destination network 192.168.2.0/24. However, the success of any returning packets going from PC3 to PC1 depends upon whether or not the routers involved have a route to the return path, PC1S 172.16.3.0/24 network. Using Principle 3 as guidance, we will configure proper static routes on the other routers to make sure they have routes back to the 172.16.3.0/24 network. Applying the principles. With these principles in mind, how would you answer the questions we posed regarding packets that originate from PC1? 1. Would packets from PC1 reach their destination? In this case, packets destined for 172.16.1.0/24 and 192.168.1.0/24 networks would reach their destination. This is because router R1 has a route to these networks through R2. When packets reach router R2, these networks are directly connected on R2 and are routed using its routing table. Packets destined for 192.168.2.0/24 network would not reach their destination. R1 has a static route to this network through R2. However, when R2 receives a packet, it will drop it because R2 does not yet contain a route for this network in its routing table. 2. Does this mean that any packets from these networks destined for 172.16.3.0/24 network will reach their destination? If R2 or R3 receives a packet destined for 172.16.3.0/24, the packet will not reach its destination, because neither router has a route to the 172.16.3.0/24 network. With the commands shown in the figure, all routers now have routes to all remote networks. Examine the routing tables in the figure to verify that all routers now have routes to all remote networks. Connectivity can be further verified by pinging remote router interfaces from router R1, as shown in the figure. Full connectivity is now achieved for the devices in our topology. Any PC, on any LAN, can now access PCs on all other LANs. Recursive route lookup. Before any packet is forwarded by a router, the routing table process must determine the exit interface to use to forward the packet. This is known as route resolvability. Let's examine this process by looking at the routing table for R1 in the figure. R1 has a static route for the remote network 192.168.2.0/24, which forwards all packets to the next hop IP address 172.16.2.2. Finding a route is only the first step in the lookup process. R1 must determine how to reach the next hop IP address 172.16.2.2. It will do a second search looking for a match for 172.16.2.2. In this case, the IP address 172.16.2.2 matches the route for the directly connected network 172.16.2.0/24. The 172.16.2.0 route is a directly connected network with the exit interface serial 0/0/0. This lookup tells the routing table process that this packet will be forwarded out that interface. Therefore, it actually takes two routing table lookup processes to forward any packet to the 192.168.2.0/24 network. When the router has to perform multiple lookups in the routing table before forwarding a packet, it is performing a process known as a recursive lookup. In this example, 1. The packet's destination IP address is matched to the static route 192.168.2.0/24 with the next hop IP address 172.16.2.2. 2. The next hop IP address of the static route, 172.16.2.2, is matched to the directly connected network 172.168.2.0/24 with the exit interface of serial 0/0/0. Every route that references only a next hop IP address, and does not reference an exit interface, must have the next hop IP address resolved using another route on the routing table that has an exit interface. Typically, these routes are resolved to routes in the routing table that are directly connected networks, because these entries will always contain an exit interface. We will see in the next section that static routes can be configured with an exit interface. This means that they do not need to be resolved using another route entry. Exit interface is down. Let's consider what would happen if an exit interface goes down. For example, what would happen to our 1S static route to 192.16.2.0/24 if its serial 0/0/0 interface went down? If the static route cannot be resolved to an exit interface, in this case serial 0/0/0, the static route is removed from the routing table. Examine this process with debug IP routing on R1 and then configure the serial 0/0/0 to shut down, as shown. Notice from the debug output that all three static routes were deleted when the serial 0/0/0 interface was shut down. They were deleted because all three static routes were resolved to serial 0/0/0. However, the static routes are still in the R1S running configuration. If the interface comes back up, is enabled again with no shutdown, the iOS routing table process will reinstall these static routes back into the routing table.